In this video, we're going to look at the convergence of a recursive sequence. Show that the sequence an defined recursively as a1 equals 2, an plus 1 is equal to 1/2 of an plus 4 converges. Let's compute a few terms of this sequence. a1 is equal to 2, a2 is equal to 1/2 of a1 plus 4, but a1 is equal to 2, so we get 2 plus 4, that's 6 over 2 is 3. Now let's look at a3. a3 is equal to 1/2 of a2 plus 4, and we computed a2 to be 3, so we get 1/2 of 3 plus 4, which is 7. That gives us 3.5. Now let's look at a4. a4 is equal to 1/2 of a3 plus 4. So we get 1/2. a3 was computed to be 3.5 plus 4. So we have 4 plus 3.5, which is 7.5, divided by 2. That's going to give us 3.75. Now let's look at a5. a5 is equal to 1/2 of a4 plus 4. This is equal to 1/2, and a4 was computed to be 3.75 plus 4, and this computes to 3.875. So let's write down a few terms that we have computed. a1, that was given to be 2. a2 is equal to 3, and we computed all of these recursively using the recurrence relationship. a3 is equal to 3.5. a4 is equal to 3.75. a5 is equal to 3.875. So the first 5 terms of this sequence suggest that the sequence is increasing and bounded above by m equals 4. So m equals 4 seems to be an upper bound. Of course, we have to verify this formally. Upper bound, and it seems that this sequence is increasing. an is increasing. All right, let's formally verify our intuition by applying mathematical induction. So we're going to apply induction. Now, let's prove that an plus 1 is larger than an. That means that every successive term is bigger than the previous term. For all n larger or equal to 1. So a1 is equal to 2, a2 is equal to 3. So clearly a2 is bigger than a1, since 3 is bigger than 2. So the result holds for n equals 1. So n equals 1 holds. Let's assume that an plus 1 is larger than an is true for n equals k. We need to prove that that this also holds for n equals k plus 1. That's the whole process of induction. So we have ak plus 1 larger than ak by assumption. Now let's add 4 to both sides. So we get ak plus 1 plus 4 larger than ak plus 4. Now you might ask, why do you add 4 to both sides? Why not another number? The reason is, of course, we're trying to work with our recurrence relationship, which is right here, an plus 1 is equal to 1/2 an plus 4. So now let's multiply both sides by 1/2. So 1/2 multiplied on the left-hand side, 1/2 on the right-hand side, and we're going to get 1/2 of ak plus 1 plus 4 is larger than 1/2 of ak plus 4. Now, you will notice that this part here, the expression on the right, is ak plus 1. That's our recurrence relationship. ak plus 1 is 1/2 ak plus 4. Increase the index by 1, this expression is ak plus 2. Because ak plus 2 is going to be 1/2 times ak plus 1 plus 4. So what we have what we have proven is that AK plus 1, which is 1/2 AK plus 4, and AK plus 2, which is 1/2 of AK plus 1 plus 4. And in the previous page, we proved that AK plus 2 is larger than AK plus 1. So we have proven that AK plus 2 is larger than AK plus 1. I need to write this as a subscript, so let me write it as AK plus 2 larger than AK plus 1. So what we have shown is that AN plus 1 is larger than AN is true for n equals k plus 1. Let me show that. If you put n equals k plus 1, we get a subscript k plus 1 is larger than an, which is k plus 1. So we get ak plus 2 larger than ak plus 1. We've proven that this holds for n equals k plus 1. But by assumption, an plus 1 is larger than an is also true for n equals k. And this is how induction works. So by mathematical induction, an plus 1 is larger than an for all n. So now we need to verify that the sequence is bounded above by m equals 4. So now prove that an is bounded above by m equals 4. So that means it has an upper bound. That is, an is less than 4. Why would we be interested in proving that it's bounded above? Well, we want to say that this sequence is monotonically monotonic and it's also bounded, and a bounded monotonic sequence will converge. So in the first part, we showed that the sequence was monotonically increasing. Now we want to show that it has an upper bound of 4. So let's start by, we know that this sequence is increasing. So the sequence an, must have a lower bound. That means an is larger than a1 equals 2. And that's our starting point, which is a1 equals 2. And this holds for all n. So we can say that the sequence an has a lower bound. L equals 2. Let's apply induction to prove that it has an upper bound where an is less than 4 for all n. Now, recall that the recurrence formula is an plus 1 is equal to 1/2 of an plus 4. Now, and a1 is equal to 2. So let's start with a1 equals 2. This is less than 4. So the result holds for n equals 1. N equals 1 works. Let's assume that an is less than 4 holds for n equals k. And our job, of course, is to prove that it also works for n equals k plus 1. That's how induction works. So ak is less than 4 by assumption. Let's add 4 to both sides. AK plus 4 is AK is less than 4, so 4 plus 4, that's 8. So now multiply by 1/2, we get 1/2 of AK plus 4 is less than 1/2 of 8. So 1/2 of AK plus 4 is less than 4. But this is AK plus 1 by definition. This is the recurrence relationship that we have. AK plus 1, therefore, is less than 4. So that means an less than 4 holds for n equals k plus 1. But by assumption, an less than 4 also holds for n equals k. So what we have shown is that an less than 4 is true for n equals k plus 1, since an is less than 4, is also true for n equals k. By induction, by mathematical induction, an is less than 4 for all n. Therefore, m equals 4 is an upper bound for the sequence. Upper bound for the sequence an. We've proven that the sequence an is monotonically increasing, so it's monotonically increasing, and is bounded above by 4, bounded above, it has an upper bound by m equals 4. So therefore, the sequence an must converge. It must have a converging limit. Let's call that P. Must converge to a limit. And we'll just call it P. The question is, what is P? Well, P is going to be the limit as n goes to infinity of an. Let's use a recursive relationship to find P. So we have an plus 1 is equal to 1/2 of an plus 4. We have a1 is equal to 2. Let's take the limit of both sides, limit as n goes to infinity of an plus 1 is equal to limit as n goes to infinity 1/2 of an plus 4. Now, we know that a limit as n goes to infinity of an is equal to p. Therefore, the limit of an plus 1 as n goes to infinity is also going to be p, because when n goes to infinity, n plus 1 also goes to infinity. So when the sequence approaches, the terms of the sequence approaches p, an approaches p, an plus 1 also approaches p. So the left-hand side expression is going to be just p. The limit of an plus 1 is equal to 1/2, and the limit of an, this is also p. So 1/2 times p plus 4. And now we're going to solve for p. This is just going to be algebra. So cross multiply, and we're going to get 2p is equal to p plus 4. Subtract p from both sides, and we get p is equal to 4. That means the sequence an converges to 4, as we predicted based on our intuition, converges to 4. All right, thanks.